Manufacturers have gone to variable valve timing or variable cam timing, or one more for you, independent cam timing, timing of each camshaft intake and exhaust for different benefits. And mostly it's power, performance that the customer wants, and reduced emissions with increased fuel economy. We also get power and torque improvements when we use the independent variable cam timing. Now, on a normal engine at any given speed and load, increasing the intake of the air into the combustion chamber, bringing more air into the combustion chamber, is going to allow the engine to burn more fuel. And that, of course, gives us more power. This is measured in terms of the engine's volumetric efficiency. And the VE, or volumetric efficiency, is simply how much air did we take in versus how much could we have fit in. Now, during engine operation, there's going to be pressure pulses in both the intake and the exhaust system, in both the intake and the exhaust manifolds. Now, this is caused by the opening and closing of the valves. We see some charts on the bottom here. On the left we see intake pulses, and on the right we see exhaust pulses. We're not trying to do any test here. We're not trying to do any measurement. We're just showing you that, for example, on the right, the exhaust doesn't flow evenly out the manifold. It actually has pulses from the valves opening and closing. Now, in order to get the best power and torque, and to say it another way, to have the highest volumetric efficiency at any given operating range, at any given engine RPM versus load, the valve events should be in sync with these pulses. On a fixed engine, a fixed cam engine, unfortunately the frequency, the magnitude, and the timing of these pulses change and vary with speed and load, so we can't compensate for them. The volumetric efficiency of an engine with a fixed valve timing is only going to be optimized at one speed. With a dual independent camshaft timing, the engine can be optimized, in fact, at any speed we have, any load that we have. This gives us improvement in low speed torque, and then again it helps us improve the top end performance while giving us a much flatter torque curve. In the graph in the bottom right we see the red line, and that's telling us that RPM is ever increasing in this example, while in the blue line the torque is a much flatter curve than we're used to seeing. Now, we also can improve fuel economy with cam timing. The control of the valve overlap is a key factor in this. Now, valve overlap is the point near piston top dead center where we have an intake and an exhaust valve open at the same time. The graph in the bottom shows the red color graph that represents the exhaust valves, while the bluish one represents the intake. And we can see that it's just not one line for each, it's multiple, showing that we can vary it. In order to get good fuel economy at low speeds, valve overlap is going to be used to reintroduce the exhaust gases into the combustion chamber. We don't need an EGR any longer. This is known as internal gas recirculation, or simply put, internal EGR. Once again, we don't need an EGR to improve the NOx coming out the tailpipe. For example, here we can see that we have a tailpipe pumping stuff into the atmosphere. In this picture we can't tell exactly what's in it, but it sure looks like some bad stuff. In order to reduce HC and NOx coming out of the tailpipe, VVT, variable cam timing, variable valve timing, can give us internal EGR.